In this video, I introduce nonlinear independent component estimation. We want to find a transformation f(x) of data x to a latent variable h in the latent space so that the latent variables hd are independent. By using chain rule, we can express joint probability of h as a product of independent probabilities of hd. Considering a change of variable h, using the change of variable rule, we have this normalizing flow. Namely, likelihood at x is equal to the prior normalized by Jacobian determinant, which can be rewritten as a log likelihood equivalently. Namely, log likelihood at x is equal to log prior plus log determinant, where this is the determinant of Jacobian matrix. A transformation F is invertible and can produce a good representation pH of data x in the latent space. This inference model and this sample model or generative model. We can use this forward path to generate a new distribution. The goal is to learn a nonlinear transformation F that maximizing log likelihood on the training data set. This log likelihood is equal to sum of two terms. First term encourages contraction in the latent space. According to the definition of this prior, because this term is smaller than 1. A small number d makes this prior larger. So we need to select a minimum number of independent components hd to this term larger. A second term encourages expansion because we need this prior contains the true posterior p to cover the training data set, which is called nonlinear independent component estimation, which learns the invertible pre-processing transform of the data set. To make the log determinant easily compute, Jacobian matrix of transformation can be diagonal, lower triangular, or upper triangular. For example, the determinant of a triangular Jacobian matrix is equal to product of his diagonal elements. Suppose that I1 and I2 are two blocks of d-dimensional vector, such that d is the size of a first block and M is a neural network. We define output Y in this formulation. Namely, it's a Y I1 is equal to X I1, and Y I2 is calculated from a function G, whose input is X I2 and M X I1. Where G is the invertible mapping. For I1 takes 1 to D, and I2 takes from D to capital D. Jacobian is a triangular matrix here. Since this is the identity matrix of size D, so the Jacobian is equal to value of this element. The inverse mapping is here. As a special case, additive coupling layer this G is equal to xi2 plus mxi1. So we have this mapping and inverse mapping here. Since this derivative is equal to 1, so the Jacobian determinant is 1, namely, it's a volume preserving, which means no expansion at all. To solve this problem, we introduce a diagonal scaling matrix S that is related to principal component analysis. So the log determinant becomes log SII. So we use it for expansion. If prior is a Gaussian distribution, so we can calculate the first term in the log likelihood is here. So we can substitute this log prior and log determinant into log likelihood. And then now we can use stochastic gradient method, descent method to train the model. For more details, please check with these references. Thank you. Bye.